The open chain form of cyclobutane, simply butane, has 2 more hydrogens. So we've seen this molecule before several times. We see it has 6 hydrogens on the ends and 4 hydrogens in the middle. So the formula of butane in the open chain form is C4H10. So we lost 2 hydrogens in tying 2 of the ring carbons together. And that's an important fact to keep in mind. So looking at this formula here, we calculate what are called degrees of unsaturation in order to determine this. So the degrees of unsaturation are equal to the number of hydrogens that we would observe in a structure with only carbon and hydrogen in it. That's this 2n plus 2. Notice that for open chain butane, C4H10, 10 is 4 times 2 plus 2, hence the 2 times the number of carbons plus 2. For each nitrogen, we add 1. For each halogen, we take 1 away, and then we subtract from that number the number of hydrogens in our actual structure. Dividing that by 2 then gives us the degrees of unsaturation of the compound, and what this will tell you is the number of rings or multiple bonds in your structure. So for instance, if you're charged with doing a spectroscopic analysis, which if you go on to higher levels of chemistry, you'll definitely have to do, you can immediately, if you see a degree of unsaturation, you can begin to think about certain functional groups. For instance, if you see 4 degrees of unsaturation, that's often a signal for the benzene group. And then you can look on your spectra to try to pinpoint where a benzene might be found and if there might be one in your molecule based on spectroscopic signals. So I wanted to work through an example here really quick of this cyclic enamine here that I've got in the bottom right. So this cyclic enamine, if we look at it and draw in all of the hydrogens, we see that we have 5 carbons, we have 1 nitrogen, and we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So there's our molecular formula. Now the question is, can we calculate the degrees of unsaturation from this, and how would we go about doing that? Well, we have 5 carbons, so we would take 2 times 5 plus 2 plus the number of nitrogens. We see we have 1 nitrogen, so we'll add 1 to that, excuse me. No halogens, so we don't have to worry about that. And then we subtract off 8 and divide that entire quantity by 2. So doing the math, we have 2 times 5 plus 2 is 12, plus 1 is 13, minus 8 gives us, I think I've made a mistake. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8. 8, 5 carbons. There it is. Forgot to draw on a hydrogen. Alright, so in fact we have 9 hydrogens in the structure. Apologies for the confusion there. 2 times 5 plus 2 plus 1 minus 9 now gives us 12, 13 minus 9 is 4 over 2, which comes out to 2. So we see that given that molecular formula, we can expect 2 degrees of unsaturation in the structure. And sure enough, if you look at the structure given here, we see there are 2 degrees of unsaturation. So looking at this structure, we have 1 degree of unsaturation that corresponds to the ring structure, and then another one that corresponds to the double bond within the ring. So using those 2 degrees of unsaturation, that can guide our thinking to think, well, we probably have a ring of some sort, and perhaps we have either 2 rings, or 1 ring and a double bond, or 2 double bonds, and then we can go to spectra to help us flesh out that distinction further. Alright, so now I wanted to jump right into the heat of things and start talking about cyclopropane. Cyclopropane is the smallest member of the cycloalkanes. It consists of 3 carbons arranged in an equilateral triangle. One thing you might notice about cyclopropane that's a little bit weird is that the necessary bond angles for cyclopropane to form as an equilateral triangle are extremely strained relative to what we're used to. So cyclopropane's carbon bond network looks like this, and if this triangle is equilateral, it's not really as I've drawn it here, but the bond angles would have to be about 60 degrees. That's a far cry if we're going to invoke sp3 hybridization at those carbons, which you would expect based on the number of hydrogens. It's a far cry from the 109.5 degrees that you're used to seeing for tetrahedral carbons. So the question is, how does cyclopropane achieve this geometry? And we can really think about that question in terms of molecular orbitals, which is why I wanted to cover cyclopropane. We're going to apply what we've learned from the molecular orbital section in Chapter 1 to a study of the cyclopropane molecule. So the original picture was this banana bond idea, that the molecules were, or the carbon atoms were sp3 hybridized, but the bonds were just less than ideal. So rather than having perfect sigma-type overlap, as we would have in a perfectly head-on bond, the bonds were slightly bent. And those bent bonds were weaker than your typical normal alkane or cycloalkane bonds, and that was a consequence of what's called ring strain in the molecule, the fact that we had to get that 60-degree angle between those carbons. And they were called banana bonds because the bonds kind of curved, so they look a little bit like bananas. However, not long after this picture came out, it was realized that it doesn't really tell the whole story. And I won't go into every detail of why this picture is insufficient, but one that you can understand based on what we've already talked about is this idea that the cyclopropyl methyl cation was unusually stable. So we would expect that cation to be extremely reactive, right, with the cyclopropyl group inducing ring strain, and with the positive charge, we would expect that molecule to be quite reactive. But as it turns out, it wasn't as reactive as chemists expected, and so something is going on here in terms of stabilization of that molecule. And when chemists think stabilization, when organic chemists think about stabilization, one of the first things that comes to mind is the idea of resonance. And you see, I've drawn kind of a weird resonance picture here for this molecule. What I've drawn is the movement of a sigma bond towards that positive charge. So you can see the curved arrow shows the movement of electrons towards the positive charge with the movement of the cation. So this isn't a typical resonance structure. In fact, it looks like a chemical reaction. But looking at the molecular orbitals of cyclopropane, as they were sort of reevaluated from this banana bond picture, you'll see how we can achieve this kind of overlap. The new model that was developed by a guy named Walsh back in 1947, I believe. And his idea was to take methylene, which is a CH2 group. It's CH2 with a lone pair. So it's carbon in a rare 2 oxidation state. From the Lewis model perspective, it looks like that, and you can see the molecular orbitals above. His idea was to take methylene, take 3 of them, combine them together, and see if we can get the molecular orbitals of cyclopropane. And in fact, he was successful. The details of this procedure are sort of beyond the scope of the course, but what's important to take home is how we can interpret Walsh's molecular orbitals to explain things, in particular this idea of resonance with the cyclopropyl methyl cation.